vectors. Our goals of today's lecture is what it means subspaces be orthogonal. Also our goals is what it means any basis be orthogonal. Actually today's goal of my lecture is what is the geometry of orthogonal vector, and the idea of two orthogonal vector is such type. Consider a right angle triangle. This is one vector. This is the vector of length x, and this is the vector of length y, and this is the vector of length x plus y, and this the angle would be 90 degree because I have considered a right angle triangle. Then by Pythagoras law, we all of us know norm of x plus y whole square equal to norm of x square plus norm of y square. We all of us know by Pythagoras law norm of x plus y whole square would be equal to norm of x square plus norm of y square. Now we all of us know norm of x plus y whole square means inner product x plus y with x plus y. That means this would be x plus y transpose times x plus y, and norm of x square means x transpose x, and norm of y square means y transpose y. Now apply distributive law, then this would be x transpose x plus x transpose y plus y transpose y plus y transpose x, which is equal to x transpose x plus y transpose y. Just omit, sorry, here y, this part. Then x transpose y equal plus y transpose x equal to 0, and this vector always would be applied for real vector. So obviously x transpose y and y transpose x always similar. So this imply 2x transpose y equal to 0. That means 2 times inner product x with y equal to 0. And from this expression we can write inner product x with y equal to 0 vector. Are you getting? So by this idea, definition is such type: let u and v be the vector in an inner product space V. Then these two vectors are orthogonal if inner product u with v equal to 0 vector. Okay? This is the actual definition of orthogonal vector. As for example, in R3, consider two vectors u1 equal to 1 2 1 and u2 equal to 2 5 4. And consider another vector w equal to 3 minus 2 1. Then notice inner product w with u1. By definition, this is actually u1 transpose time w. This would be 3 minus 4 plus 1, which is equal to 0. And inner product w with u2 also equal to 0. So obviously this vector is perpendicular or orthogonal to u1, and this vector w is also orthogonal to u2. Are you getting the actual idea of orthogonal of two vectors? Now consider one vector which is denoted as x in R4, who is defined as such type 1 1 1 1. Then let us find all vectors in R4 which are orthogonal to x. For this, consider an arbitrary vector which is denoted as u, as u1, u2, u3, u4, which is orthogonal to this vector x. Okay? That means that imply inner product x with u equal to 0 vector. That means 1 1 1 1 dot u1, u2, u3, u4 equal to 0, and that implies u1 plus u2 plus u3 plus u4 equal to 0. That means those vector be orthogonal to this x whose sum of each component be 0. That means you must be of the from set of those vector which is look like alpha, beta, gamma, minus alpha, minus beta, minus gamma, where alpha, beta, gamma belongs to R. I will see generalize of this example. What it means? One subspace is orthogonal to another subspace. The idea is we say that two vector subspace V1 and V2 of an inner product space are orthogonal if V1 is perpendicular to V2 for all V1 belongs to capital V1 and for all V2 belongs to V2, capital V2. Then we shall denote these two subspace mean capital V1 and capital V2. Both are perpendicular to each other. That means the actual idea is every vector of V1 is orthogonal to every vector of V2. This is the idea of when two subspace be orthogonal. As for example, consider V equal to R5 with standard inner product and consider one subspace V1 equal to such type set of those elements x, y and other component b0, 0, 0 where xy belongs to R, and consider another subspace V2 equal to set of those elements 0, 0 R, s, 0 where R and s belongs to real number. And notice obviously the subspace V1 is perpendicular to V2 because inner product xy 0, 0, 0 with 0, 0 R, s, 0 is obviously equal to 0 vector. So obviously this subspace be orthogonal to each other. Are you getting the idea? And if we consider the subspace V3 equal to 0, 0, 0 z where z belongs to R, obviously this subspace is perpendicular to V1, V3 is perpendicular to V1. Also similarly V3 is perpendicular to V2. Have you understood? When two subspace be perpendicular? Now I will see the new idea, orthogonal complement of a subspace. Consider V be an inner product space and W be a subspace of the vector space V. Then orthogonal complement of W is denoted as W per. This is actually those set such be in the subspace capital V such that inner product V with W equal to 0 where for all W belongs to the subspace capital W. Okay? That means actual idea is orthogonal complement of W per is set of those vector of V who is perpendicular to all vector of W. Are you getting the idea? Well, that means as for example, see the previous example, V equal to R5 with standard inner product and consider the subspace V1 equal to xy 0, 0, 0 where xy belongs to R. Then V1 per means orthogonal complement of V1 would be such type set of those vector which look like 0 0 A comma B comma C where A B C belongs to R. This proof will be such type if A1 comma A2 comma A3 comma A4 comma A5 belongs to V1 part. That means inner product of A1 comma A2 comma A3 comma A4 comma A5 with the vector subspace x comma y comma 0 comma 0 comma 0 equal to 0 vector. And from this expression, this imply a1x plus a2y equal to 0 for all xy belongs to R. And from this line we can tell, obviously a1 equal to 0 and a2 equal to 0. That means V1 part would be such type 0 0 A comma B comma C where A B C belongs to R. Are you getting the idea how we have to find orthogonal complement of any subspace? Say new type of expression about complement of a subspace. Consider V be an inner product space and W be subspace of the vector space V. Then W part means complement of W obviously be subspace of the vector space V, and W intersection W part always contain 0 vector. The proof is such type, we all of us know W part contains set of those vector in the vector space V such that inner product V with W equal to 0, where this is true for all W belongs to capital W. This at first we have to check W part be a non-empty set. For consider 0 belongs to W part, then take any arbitrary element small w belongs to capital W, then inner product 0 with this small w obviously equal to 0, and this is true for all small w belongs to the subspace capital W, because inner product 0 with all vector of capital W always will be 0. That means from this expression we can tell easily 0 belongs to W part, and since 0 belongs to W part, that imply W part be a non-empty set. Okay. Now consider two vector v1 v2 belongs to W part, and we have to check their sum belongs to W part. For this, consider an arbitrary element W belongs to the subspace capital W, then inner product v1 plus v2 with small w equal to, by the distributive property, this is equal to v1 with w plus v2 with w. And since I have considered v1 v2 belongs to W part, so obviously v1 with w equal to 0 and v2 with w equal to 0, because small w belongs to capital W. Okay. And since inner product v1 plus v2 with w equal to 0 vector, that imply v1 plus v2 belongs to W part. Second, take arbitrary element v1 belongs to W part. We have to check alpha v belongs to W part. For this, take alpha belongs to any real number, be a scalar, and consider similar to before one vector, arbitrary vector W belongs to capital W. Then inner product alpha v1 with W equal to, by the property of scalar multiplication, this is equal to alpha times inner product v1 with W. And since v1 belongs to W part, that means inner product v1 with W equal to 0. That means this is equal to alpha times 0 equal to 0. And since inner product alpha v1 with W equal to 0, So obviously alpha b1 belongs to W par. Therefore I have proved W1 be a non-empty set. Then I have proved two arbitrary vector. If we consider two arbitrary vector v1 v2 belongs to W par, then their sum also belongs to W par. And I have proved scalar multiplication of any vector also belongs to W par. That means obviously W par be a subspace of the vector space V. Are you getting the proof? Oh well. Our next property, W intersection W par always would be singleton set 0. And this is obviously very easy type property, just prove oneself. Now I will see this expression by some example. As for example, consider W be xy plane in R3. Then find the W par. This is the xy plane in R3. That means these subspaces look like xy0 and we have to find W par. Consider W par be any arbitrary vector ABC. Then inner product W with W par would be 0 vector. That means that imply xy0 with ABC equal to 0 vector. And from this expression, this is, since this is R3, that means inner product mean here dot product. That means this imply AX plus BY equal to 0. That imply A equal to 0 and B equal to 0. That means W bar B, the vector which look like 0, 0, C, and this is nothing but only z-axis. Therefore, the orthogonal complement of xy plane will be z-axis. Okay? Notice one thing. W intersection W par here contain only 0 vector. Okay? Now I will see. We all of us know the column space and null space. Consider this as column space of A transpose. This is always perpendicular to null space of A. Okay? And notice here every vector of column space of A transpose means obviously row space. Every vector of row space is perpendicular to null space. And angle between row space and null space is obviously 90 degree. So, row space and null space are actually orthogonal to each other. That means the orthogonal complement of null space of A is all vectors that perpendicular to null space of A, and which is actually column space of A transpose, that means row space. Therefore, the orthogonal complement of null space of A, which is denoted as null, this is column space of A transpose, which is actually row space. Now I will just discuss this idea why the orthogonal complement of null space of A is column space of A. For this, consider a M cross N matrix. Then obviously the rows of A has N components and the columns of A has M components. Then obviously columns of A subspace of Rm and column space of A transpose subspace of Rm, and null space of A transpose subspace of Rm, and null space of A obviously subspace of Rn. From this idea, from this expression, this is clearly true, since the orthogonal complement of null space of A is column space of A. For this, the actual idea is Ax equal to 0, where this is the row 1, this is row 2 and this is row M, and here the column vector as a x equal to 0 vector. Since null's orthogonal complement of null space is row space, that means inner product between these two vectors obviously equal to 0. That means row 1 dotted with x equal to 0 vector, row 2 dotted with x equal to 0 vector, and row m dotted with x equal to 0 vector. And that implies obviously every x here, obviously this x belongs to null space of A, is orthogonal to row space of A. And the idea is consider a arbitrary vector which is linear combination of row 1, row 2 and row m. That means the vector v equal to c1 row 1 plus c2 row 2 plus cm row m. And since dot product of row with the vector x is 0 vector, that means multiply this expression by x transpose. X transpose times v, which is equal to actually x transpose times c1 r1 plus c2 r2 up to cm rn. And since this is the scalar, so obviously omit c1, then this would be c1 times x transpose r1 plus c2 times x transpose r2 up to cm times x transpose rm. And notice, since row 1 dotted with x vector is 0, also row 2 dotted with x vector is 0, similarly row m dotted with x vector is 0. That means this is equal to c1 times 0 plus c2 times 0 plus up to cm times 0. And this is actually equal to 0 vector. That means column space of A transpose is, which is actually the row space of A, is perpendicular to null space of A, and this is actually, these two subspace are subspace of Rn. If we consider dimension of row space equal to R, then dimension of null space would be n minus R. Similarly, this I have got by the equation Ax equal to 0. If we apply Ax equal to B, then I will get column space of the matrix A. And similar to before, column space of the matrix A is perpendicular to null space of the matrix A transpose, which is actually subspace of Rm. And this picture is such type: column space of A perpendicular to left null space of the matrix A. Since dimension of row space equal to R, obviously dimension of column space equal to R, and then dimension of left null space would be, since this is subspace of Rm, so dimension of left null space would be M minus R. Now consider one example. The vector space V is spanned by the vector 1, 2, 2, 3 and 1, 3, 3, 2. Then can we write the V1 part? Here I will solve it by Ax equal to 0 solution. Here the matrix generated by the vector 1, 2, 2, 3, 1, 3, 3, 2 with here x is x1, x2, x3, x4 and here the vector 0, 0, 0, 0, 0. Now after row reducing from, it would be 1, 0, 2, 1, 2, 1, 3 minus 1, x1, x2, x3, x4 equal to 0, 0, 0, 0. And notice these are pivot of this equation of this matrix. That means since x1 and x2 are pivot and x3 and x4 be free variable, so consider x4 equal to b and x3 equal to a. Then x2 equal to minus x1 plus x3, which is equal to minus a plus b, and x1 equal to minus 2x2 minus 2x3 minus 3x4. Now put the value. Then after calculating, this value would be minus 5b. Then the vector x is written as, put the value, x2 equal to minus a plus b, x1 equal to minus 5b, ab. That means vector x is generated by a times 0 minus 1 1 0 plus b times minus 5 1 0 1. Therefore, this part be the solution of the null space of the matrix. So this is actually be the V1 part, which is spanned by these two vectors. Are you getting what is the V1 part? To find V1 part, actually we have to find the solution of null space. Are you getting? Well, I hope my all viewers will can to solve V1 part easily. Okay? Today I will stop here. In my next video, I will see what happened the basis when the bases are orthogonal. But at first I will hardly recommend you please see today's video with pay attention, because this topic is very important for any competitive exam. See you soon. Stay safe and stay positive always. Thank you so much.